Okay, I think we can start. Today we will start with new topic, which is direct current circuits. First of all, we will talk about multiple resistors and how to get equivalent resistance. You can calculate equivalent resistance of such circuits, but sometimes it becomes more complicated like this. What we have here, we have one more EMF here, another EMF and resistance here. So in that case, it becomes very complicated to calculate the equivalent resistance. So how to deal with such kind of circuits? Then we will apply Kirchhoff rules to calculate equivalent resistance and current traveling within that type of complicated circuits. And we will also talk about how to use ammeter to measure current, voltmeter, ohm meters, and potentiometers in a circuit. We will talk about also digital multimeters. And probably on Thursday for the next lecture, we will continue with resistor and capacitor circuits. So here we have a circuit, you can see that. So within that circuit, we have one resistor here and one capacitor here. This is called as RC circuit. So within RC circuits, the current is not constant. It is decreasing by time. We've discussed all these things for the next lecture. And we will also talk about electric power is distributed in the home. So this is AC electricity. We will also talk about this. Of course, concerning the AC circuits, we will not go into detail. We will just give you some information about household electricity. Let's start with the DC versus AC current. So what we mean with direct current circuits, in which the direction of the current does not change with time. So here, if we have the direction of the current, or if you have the direction of the current, for example, it does not change by time in direct current circuits. However, in alternating current circuits, the direction of the current oscillates back and forth. So this is the main difference. So what is the example for the DC circuits? Flashlights, automobile wiring systems are examples of the direct current circuits. And we use alternating current. It means that AC current in household electrical power systems. So this chapter is mainly concentrated on the DC current circuits. But at the end of the chapter, we will talk about alternating current circuits, and we will give a very short example of household electrical power systems, but we will not go into detail concerning AC circuits. But it is better to know that information, that the same principles for analyzing networks apply to both AC and DC circuits. Don't forget this one. So let's continue with resistors in series. What you see here, we have three resistors. They are connected in series and current I is passing through here. So what is the equivalent resistance of that circuit? So how to calculate it? So just try to calculate the potential difference between A point and X point. Between A and X, potential difference can be written like this: VAX, current passing through on that resistor, and then the resistance of the resistor. So again, the voltage difference between X and Y can be written like this: I times R2, and the voltage difference between Y and B can be written like this: I times R3. Is it okay? So then the voltage between A and B, the total voltage here, the potential difference between A and B can be written potential difference here plus potential difference here plus potential difference here. So if you take all these things, put here, and then finally you can get that expression. This is the current passing through the circuit. This is the resistance of the resistor 1, resistance 2, plus resistance 3. So what we have here, this is the potential difference between A and B, and this is the current passing through the circuit, and this is the total resistance of the system. This is called as equivalent resistance and given by that expression. Equivalent resistance of a series combination is given with that expression. We take the sum of the individual resistors. This is the resistors in series. So here, maybe I can remind you capacitors. Capacitors can also be connected in series or parallel. We have discussed this one in chapter 24, okay? So in capacitors, it is completely different. Don't forget this one. I strongly suggest you to check the parallel and series connection in capacitors. Then it will be very useful for you later on for complicated circuits. So now let's continue with resistors in parallel. Here we have again 3 resistors. Now they are connected in parallel. What we have here, we have current I passing through between A and B. So current is split here into 3 parts, okay, and then combined again here. So this current 1 passing through on that resistor is given by VAB over R1. So what is important here is that the voltage difference between A and B is same for this one, is same for this one, and also same for this one, okay? So since voltage difference between A and B is same, we can write current 1 by using that expression VAB over R1, current 2 VAB over R2, current 3 VAB over R3, okay? So the total current passing through that circuit, I, is given by I1 plus I2 plus I3, the total current. Then put this one here, put this one here, put this one here. So in total, you will get that kind of expression, VAB times 1 over R1 plus 1 over R2 plus 1 over R3. Or like this, I over VAB is equal to that expression. So what we have here, this is 1 over R equivalent. Then in case of parallel connection of resistors, we can write equivalent resistance like this. 1 over equivalent resistance is given by that expression. So again, it was completely different in capacitors. Don't forget this one. Do you have any question in that part? So we have seen resistors in series and resistance in parallel. So let's talk about a special case in case of parallelly connected resistors. Here we have 2 resistors connected in parallel. So the equivalent resistance can be written like this: 1 over R equivalent is equal to 1 over R1 plus 1 over R2. Then if you multiply them, you will get that expression, R1 plus R2 is over R1 times R2. Then the equivalent resistance for 2 resistors in parallel can be written like this. So then what about the VAB, the potential difference between A and B? VAB is same for this circuit, and it is also same for that path, okay? Then for this one, VAB is I1 times R1, and it is also equal to I2 times R2. If you take this one, you can get that expression I1 over R2. I2 is equal to R2 over R1. So this is a special case when two resistors are in parallel. So what do you see here? Look at that formula. If I increase R1, I mean if I increase the resistance of this resistor, if I have here huge resistance, then the current passing through that resistor will be smaller. If the resistance is higher, then the current is smaller. So it is vice versa, inversely proportional to their resistance. So now let's talk about combinations of seriously and parallelly connected resistors. So here we have one resistor and two other resistors here. These ones are connected in parallel, and this guys and this one are connected in series. So how to get equivalent resistance here? So here we have a main method to get the equivalent resistance of such circuits. Try reducing this circuit to series and parallel combinations. So what we have here, first, replace the parallel combination of R2 and R3 with its equivalent resistance. Here we have R2 and R3. So first of all, get equivalent resistance of that parallelly connected resistors, and then get equivalent resistance by using that one and that one. So this is the main way to calculate series and parallel combinations. We have another example here. Here we have two resistors which are connected in series, and here we have one more resistance which is connected parallel with that ones. So again, try reducing this circuit to series and parallel combinations. So in that case, first replace the series combination of R2 and R3 with its equivalent resistance. Here, first of all, you should solve that one and that one, then you will get equivalent resistance here in the seriously connected resistors, and then you will solve that parallel connected resistors. So now let's have a look on that example. This is the example one, first example of that chapter from the book. What we have here, we have a figure. Look at that figure. Find the equivalent resistance of the network in that figure and the current in each resistors. So what is asked? Equivalent resistance asked, and then it is the current in each resistor is also asked. The source of EMF has negligible internal resistance. So this is the circuit. Here we have an EMF which provides 18 volts, right? And internal resistance of that EMF is 0. We have discussed EMF and their internal resistance during last lecture. So here we have 4 ohm resistance. Here we have 6 ohm resistance. Here we have 3 ohm resistance. So what is asked? Equivalent resistance of the network is asked. So how to calculate? First of all, just try to calculate equivalent resistance of that two resistance. This will be calculated like this, since they are connected in parallel, 1/6 plus 1/3 ohm. Then finally, we can get the equivalent resistance of that circuit. That part is 2 ohm, okay? We have here 4 ohm. In total, we have 6 ohm. This is the equivalent resistance of the complete system. So we have 18 volt, which is coming from the EMF, right? And we have 6 ohm here. So what is the current? Current can be calculated. Current passing through within that circuit from positive to negative, which is given by 3 amp. Okay, so but this is not enough. So what was the question? The current in each resistor. So we have calculated current here. So what is the current here? What is the current here? So since we have calculated the main current within the circuit, which is given by 3 amp, we can go back to that position. So 3 amp is passing through on that resistance, and 3 amp is passing through on that combination of resistance. Okay, so 3 amp, 3 amp. So from 4 ohm, I can get that we have 12 volt here, and on that resistance we have 6 volt. 2 ohm, 3 amp, 6 volt. Okay, so in total we have 18 volt. 18 volt provided by EMF and 18 volt dissipated in the resistors. So still we didn't get the current in each resistor, so but we will continue from that point. So remember that this was like this at the beginning, this case. So the potential difference between C and B here, between C and B, is given 6 volt. We have calculated this one. So the potential difference here is 6 volt. Potential difference is here 6 volt. And we know the resistance of that resistor. We know the resistance of that resistor. So we know the potential difference. Then we can calculate 1 amp for that resistance. And we can calculate 2 amps for that resistance. So we have calculated all currents passing through on that resistances. Do you have any question in that part? Okay, if not, then let me continue. So another very nice, very useful example from the book, example 26.2. So here we have 2 identical bulbs, incandescent light bulbs, each with resistance 2 ohm. This is 2 ohm, this is also 2 ohm, are connected to a source with 8 volt EMF and negligible internal resistance. Here we have an EMF and they are connected like this. Find the current through each bulb, the potential difference across each bulb, and the power delivered to each bulb and to the entire network if the bulbs are connected in series and in parallel. So we have 2 identical bulbs. First of all, we use an EMF source which provides 8 volt, and we connect them in series like this. Okay, this is the circuit. This resistance and this resistance are connected in series. And then here again, we are using same EMF source here and same light bulbs, but now we connect them in parallel. Okay, so what you see here, that the current can pass through in that circuit, also in that place. So what is the question? The question is that find the current through each bulb. What is the current here? What is the current here? What is the current here? Then what is the potential difference across each bulb? What is the potential difference here? 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 And what is the power delivered to each bulb? Power is produced by the EMF. Also here, power produced by the EMF and then delivered to the bulbs, right? So what is the power delivered to that bulb and what is the power delivered to that bulb if they are connected in series and parallel? So this is the last question. So first of all, let's try to understand the questions. Suppose one of the bulbs burns out. Okay, for example, here, this is burned out. Okay, so what happens here? Its filament breaks and current can no longer flow through it. What happens to the other bulb in the series case, in the parallel case? So let's consider that this bulb is broken. What happens to that one? Or in parallel case, let's consider that this bulb is broken. What happens to that one? So this is the question. So then let me continue. Let's continue with series case. Here we have EMF. It has no internal resistance. It provides 8 volt. And here we have seriously connected 2 light bulbs. Each of them has 2 ohm resistance. Okay. So what was the question? Current, potential difference, power. So current is given by the potential difference between A and C and the equivalent resistance of these 2 resistors. Equivalent resistance, this is seriously connected, 2 ohms plus 2 ohms. Okay, then equivalent resistance is 4 ohm. And here we have 8 volt, then the current passing through that circuit is 2 ohm, 2 amp, sorry. So then we have calculated the current. So what was the next question? The potential difference across each bulb, potential difference between A and B, potential difference between B and C. So potential difference in both cases is given by I times R. I is, we have already calculated, which is given by 2 amps. And then here we have resistance of each resistor, then 2 ohm here, then the result is 4 volt. Okay, so the potential difference here 4 volt, potential difference here 4 volt. Now we can calculate power. Power is given by I squared times R for these resistors. We have calculated this one during the last lecture, or we can calculate power by using that expression, square of potential difference over resistance. Okay, we have done it during the last lecture. So let's calculate for this one. I is given 2 amp, take the square of this current, and then resistance is also known, this is 2 ohm. Then we can find the result, 8 watt. So 8 watt power delivered to that light bulb by that EMF source. EMF provides power. So if you use that formula, you can find again 8 watt. So in total, we have 2 light bulbs. So 8 watt delivered to that one, 8 watt delivered to that one. In total, 16 watt delivered. So who produced that 16 watt? 16 watt produced by that guy. So how to calculate this one, which is calculated by I times EMF. I is 2 amp passing through that one, 2 times 8, again 16 watt. 16 watt produced by the EMF and delivered to that light bulb and delivered to that light bulb. Is there any question here for the seriously connected light bulbs? Then let's continue with the parallel connection, same light bulbs, but the same EMF, we just connected them in parallel. So here we have the circuit, EMF, no internal resistance in the EMF, then one light bulb, another light bulb, they are connected in parallel. So here we have current, now current is split into 2 parts and then combined again here. If the bulbs are in parallel, the potential difference here between D and E across each bulb is the same and equal to 8 volt. Okay, because provided by the EMF 8 volt. So here we will have 8 volt, here we will have 8 volt. Resistance is known, potential difference is also known, 8 volt. Then you can calculate current here, you can calculate current here. Then the current is known as, calculated as 4 amp. Okay, so 4 amp here, 4 amp here, then in total 8 amp. Okay, 8 amp is traveling here in that circuit. So what is the power here? The power I squared times R, 4 amp is passing, put the 4 amp here, the resistance is already known, then the power delivered to that light bulb is given by 32 watt. Again, for this one, another 32 watt, okay? In total, 64 watt, okay? The total power delivered to that 2 light bulbs. So 64 watt power. So where we get that power? So 8 volt and 8 amp, 8 times 8, 64 watt produced by that EMF, and then dissipated, delivered to dissipated within that resistors or delivered to that resistors. So in total, what we see here that we have look at that one. This is light bulb, same light bulb here, same light bulb here, same light bulb here. What do you see in that picture? In a series connection, we can get less brightness from the bulbs, but here we have brighter light bulbs. You see that in parallel connection, because in parallel connection we have delivered 82 watts to each light bulb, but in case of series connection we have delivered just 8 watt to each light bulb. Okay, so this is the advantage of the parallel connection. You can deliver much more power. So what was the last question? Look at the example. What was the last question? Suppose one of the bulbs burns out. What happens to the other bulb in the series case? So in series case, if this bulb is broken, then now we don't have any complete circuit. Circuit is broken. We have an open circuit, so current cannot pass through within that circuit. So if this is broken, this will also be closed, okay? There will be no current passing through on that resistance. But in that case, let's consider that this is broken. Current at the beginning was traveling like this, okay? If this is broken, this will be off, but since we have current passing through on that light bulb, then this will be on, okay? So this is another advantage of the parallel connection. Here we have very common application of parallel connection of the headlights and tail lights in the cars. So hence each light is exposed to full potential difference supplied by car's electrical system, giving maximum brightness due to the parallel connection. Another advantage is that if one headlight or tail light burns out, the other one keeps shining, okay, in the cars. So same example. Do you have any question here? I will continue with Kirchhoff's rules. In the previous case, we have seen parallel connected resistors, seriously connected resistors, okay? So you can get equivalent resistance from that type of circuits. But sometimes resistor networks cannot be reduced to simple series parallel combinations. You see very complicated connections, you see. So what we will do in that cases, we will use techniques developed by Kirchhoff rules, just 2 rules, don't forget. By using that rules, we can calculate current or equivalent resistance of the complicated networks of resistors. So let's start with junction rule, Kirchhoff's junction rule. So what is junction? First of all, here we have a circuit. We have an EMF here. We have another EMF. Here we have resistor. So let's consider that current is traveling like this here. Okay. So what we have here we have a junction. Okay. If we have a current here, it will be split into 2 parts. Or if the current is coming like this, if another current is coming like this, it will be combined here. Okay, so this is a junction. Here we have another junction, okay, with the same idea. But here that point and that points are not junctions because here current continues, okay? without any dividing. So junction must be like this. The current leaving a junction equals to the current entering it. This is the Kirchhoff's junction rule. Current 1 is entering into the junction. Current 2 is entering into the junction, and the leaving current is equal to the sum of the entering currents. Okay, don't forget this. So the sum of the currents into the junction and leaving from the junction must be 0. Okay, this is the junction rule of the Kirchhoff. So it is like water pipe analogy. The flow rate of water leaving the pipe equals the flow rate entering in. Here water enters, here water enters, and water is leaving. So the flow rate of water leaving here equals to the flow rate entering here and entering here. It is same. Current, this one, and this one is equal to this one, like this. So this is the junction rule, and we have another rule, Kirchhoff's loop rule. What is loop? Loop is that one. This is another loop. This is another loop. So what is the loop rule? Kirchhoff's loop rule tells us that the total potential difference or sum of the potential differences around any loop must be 0. Here we have EMF. It has a certain potential difference, and here we have a resistor. It has certain potential difference. Here we have another resistor. It has certain potential difference. Here we have EMF. It has potential difference of E2. Okay, so the total potential difference here within that loop must be 0. Okay. This is given in the Kirchhoff's loop rule. I will go into detail. But here we have very important useful information, sign conventions for the loop rule. So you need to calculate some of the potential differences here, for example, for that loop, okay? But which one is positive, which one is negative, which one is negative, which one is positive. So how to decide this? So decision for the positive and negative contributions to the sum of the potential difference can be done by using that rules here. Look at 4 conditions. Never forget that 4 conditions, okay? Without using that information, you cannot apply Kirchhoff's loop rule. Okay, your result will be wrong if you don't know that rules. So look at that one. Here we have an EMF. This is the negative side. This is the positive side of the EMF. If the direction of the travel within the loop don't mix with the direction of the travel and direction of the current. Current can be like this. Loop can also be like this along the current, okay? Or current can be like this, or you can choose the loop direction like this, okay? So let's consider that you choose current direction like this here, and you also choose a loop direction same as the current direction, okay? So if you travel in the loop from negative to positive. So look at that one. This is the loop direction. You travel here, for example, from negative to positive. Then you will get positive EMF, okay? But here, again in the same loop, you travel here from positive to negative. Look at that EMF. You travel from positive to negative. Then if you travel from positive to negative, then the contribution from that EMF will be negative, okay? So this is the rule for the EMF sources. But what about the resistors? If the direction of the current and direction of the travel are same, then we have negative contribution to the sum of the potential difference, negative minus times R, okay? If the direction of the current passing through that circuit and the direction of the travel are opposite to each other, we will get positive one, positive contribution to that sum of the potential difference. Now I will show you one example, then you can better understand. Here we have a single loop circuit. Here we have many loops, okay? Here we have a single loop circuit, which is the example from the book, example 26.3. Here we have an EMF. Here we have another EMF. Here we have a resistor. Here we have a resistor. We have just one loop here, okay? So this is the example of leave battery one car and that battery another car, and you would like to charge that battery by using leave battery, okay? This happens during the winters. Maybe you had this one once in your life. So let's say this is the leave battery, okay? This is the that battery here, EMF, and the resistance of the cables are given here. Just you can consider like this. So what is the question here? Using the Kirchhoff's rules, we can find the current in the circuit. What is the current in the circuit? And the potential difference between A and B points. Okay, you can also calculate potential difference between that points, okay? If you say C, if you say D here, then you can also calculate VCD and the power output of the EMF of each battery. So what is the power output of that EMF? What is the power output of that EMF? You can calculate all these things by using Kirchhoff's rules. Otherwise, it is not so easy to do that. So now let's try to do that. So the question, find the current in the circuit. What is the current in the circuit? The second question, what is the potential difference between A and B points? And what is the power output of the EMF of each battery? Starting at A and traveling counterclockwise, so I choose that this is the direction of the current, okay? I consider that the current is traveling in that direction. And then I also choose a loop in the same direction of the current, okay? This is the direction of the current and this is the direction of the loop, direction of the travel, this blue one. Starting at A and traveling counterclockwise with the current, we add potential increases and decreases and equate the sum to 0 as in equation. Here we will apply that rule, okay? We will get the sum of the potential differences. So now let's start from this one. Here we have an internal resistance of the EMF and current I is passing in that direction. The loop direction is also same with the current. So for the resistors, if the direction of the current and direction of the travel are same, then we will get negative here. I times 4 ohm from that resistor. Look at that one. Travel in current direction. From the resistors, we will get negative 1. So let's continue. Here we have 4 volt EMF, but look at the direction of the travel. The travel from positive to negative. From positive to negative, then we will get negative contribution to the sum. Negative 4 volt from that EMF. Now we are here. So this is the direction of the current. This is the direction of the travel. They are in the same direction, negative I times 7 ohm. So look at that one. the direction of the travel for the EMF from negative to positive. From negative to positive. If you travel from negative to positive in EMFs, then we will get positive one. So now here we have positive 12 volt from that EMF source. And we have internal resistance of that EMF here, which is given by 2 ohm. The direction of the current, direction of the travel, they are same. So minus I times 2 ohm here. And here we have another resistor, direction of the current, direction of the travel, or direction of the loop, minus I times 3 ohm. All the voltage contributions must be equal to 0 according to the Kirchhoff's loop rule. Then I can get 8 volt is equal to I times 16 ohm. Then the current within the circuit can be calculated by 0.5 amp. Any question in that part? This is the application of the Kirchhoff's loop rule. Then what was the second question? The second question is, what is the potential difference between A and B? Okay, the potential difference between A and B. You can apply Kirchhoff's loop rule, start from that one and go to in that direction. This is the direction of the current. This is the direction of the loop. Then you can calculate, or you can start from B and go to A, okay? So again, you can calculate the potential difference between A and B. So let's go from B to A. This is the direction of the current. Now we are going from B to E. This is the direction of the travel. Now we have an opposite travel, you see? So here, current in that direction, travel in that direction. Then we have positive current times resistance. So here current we have calculated 0.5 amp and resistance is 7 ohm. Here we have travel direction from negative to positive in that EMF, okay? From negative to positive, we should have positive contribution to the Kirchhoff's rule, okay? So then here we have another resistor, 4 ohm resistor, direction of the travel. This is the direction of the current. Direction of the travel and direction of the current are opposite to each other. So we have positive contribution. In total, we have 9.5 volt. So it is not equal to 0 because it is not the closed loop, okay? So we are just going from B to A. But if you are going from B to B, then in total it must be 0. If you are going from A to A or A to A in that direction, in total it must be 0. But we are going from B to A or A to B, we will have some certain voltage, okay? Or sometimes even this one can also be 0 depending on the direction of the EMF and direction of the current. So then what was the power output of the EMF of each battery? So what is the power here? What is the power here? So power of this 12 volt EMF is given by EMF times current, 12 volt times 0.5, 6 watt. And here we have 4 volt EMF. The voltage the EMF is given by 4 volt times the current, it is 2 watt, okay? So 6 watt produced by that guy and 2 watt spent by that battery in order to charge that battery by using this leave battery, okay? So we have 4 watt more to spend. The other 4 watt is spent here, 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 and here. Okay? Any question here? Any question? So then let me continue with charging a battery. This is example 26.4 from the book. Let me read the question first of all, and then try to solve it. In the circuit shown here, a 12-volt power supply with unknown internal resistance. This internal resistance R is unknown. It is connected to a rundown rechargeable battery with unknown EMF and internal resistance 1 ohm. Here we have another battery. This is a rundown rechargeable battery. It has internal resistance of 1 ohm, but the EMF is unknown, okay? And there is here an indicator light bulb of 3 ohm. Here we have resistor. The resistance of the resistor is 3 ohm, carrying a current of 2 amp. Here we have 2 amp. The current through the rundown battery is 1 amp, okay? 2 amp is passing here and 1 amp is passing here in that direction. So the current, okay, find internal resistance, find the EMF of this one, and the current through the power supply. So what is the current here? Okay, this is the question. In order to find the current here, we can apply the Kirchhoff's first rule. Look at that rule here. Kirchhoff's junction rule. The total current in the junction must be 0. Entering currents must be equal to the leaving currents. Okay. Then now let's look at the example. Here, junction A here, okay, 1 amp current is entering from that point and 2 amp current entering from that point. So here you can get 3 amp, okay, applying Kirchhoff's junction rule, okay. So output current must be equal to the entering or input currents, okay. So if you consider that these input currents are positive and this one is negative, if you put them into the Kirchhoff's junction rule, then you can get this expression. This is the leaving from the junction, negative I, we don't know it, okay? And these are the entering currents into the junction, these are positive. Entering ones are positive, leaving one is negative. Then in total, they are 0, okay, according to the Kirchhoff's junction rule. So then you can calculate current is 3 amp from that equation. So we have calculated the current. It is 3 amp. We have another 2 unknowns. One is internal resistance of this EMF, and the other one is EMF of this battery. So how to calculate it? We can apply loop rule. Here you can choose 3 loops. One loop can be like this. Okay, this first loop. Direction you choose yourself. You can also choose opposite. It depends on you, okay? So direction is this one. Or you can choose this loop here. This is another closed circuit. Here you can choose another loop. So here we have 3 loops. By using that loops and applying Kirchhoff's loop rule, you can get that unknown values. So now let's have a look the large outer loop, this loop. Start from the EMF from negative to positive. Then it will be positive 12 volt here. And here we have internal resistance. We don't know the value of the resistance, but we know the current. We have calculated 3 amp is passing here. Since the direction of the current and direction of the loop here, direction of the travel are same, we will have negative 3 amp times R. And here, just continue. Here we have another resistor. This is the direction of the current. and direction of the travel, they are same. It will be negative again, negative 2 amp times 3 ohm. So the sum of the potential difference will be 0 according to the loop rule. Okay, so here we have only one unknown, R, then you can calculate it, 2 ohm. So we have found the internal resistance of the EMF source. So now, how to calculate this one? In order to calculate this one, you can use that loop or you can use that loop. Okay, it depends on you. So let's use that loop. So this is the travel direction. Here, travel from positive to negative, then negative contribution from that EMF. And here, this is the direction of the current. Travel here is opposite to the current. Then positive contribution from this one, 1 amp times 1 ohm. And here, travel and current are in the same direction. So negative contribution from this one, negative 2 amp times 3 ohm. They are equal to 0 in total. It comes from the loop rule. So then we can calculate the magnitude of EMF. It is given by -5 volt. So what is the meaning of -5? The negative value for the EMF shows that the actual polarity of this EMF is opposite to that shown here. Let me write like this. Actually, it should be like this. Okay, the direction of the EMF here must be like this. For this reason, we have found -5. You can also understand from the direction of the current. We have done it in EMF sources during the last lecture. If the direction of the current in the EMF from negative to positive, then it means that this provides an output power. If the direction of the current from positive to negative in the EMF, then this gets power. I mean, this is charging. We have done it during the last lecture. So we can also calculate the voltage difference between B and A, okay, by using that one or by using that one or by using that one. Potential difference will be equal to this one and this one. They will be same. So in order to calculate potential difference between B and A, I can use that expression. So by using that circuit, here I have 2 amp and 3 ohm, then I can get 6 volt. So 6 volt potential difference is also valid for this one, also valid for this one. So now, do you have any question here? Any question in that part? Okay. Now, power in a battery charging circuit. In the circuit of example 26.4, in the same circuit here, find the power delivered by 12 volt power supply and by the battery being charged. So what is the power here? What is the power here? And find the power dissipated in each resistor. So power will be dissipated here, power will be dissipated here, power will be dissipated here, power will also be dissipated here to charge that EMF, and this is the only source of the power, okay, within that circuit. So power of this EMF source can be calculated by using EMF times current. Current, we have found it in the previous example, 3 amp passing through that EMF. Then it provides 36 watt, okay? 36 watt. But here we have a resistance which has 2 ohm, okay, 2 ohm resistance, and current 3 amp is passing through that resistance. So some part of the produced power will be dissipated on that resistor. So this dissipated power, 18 watt, okay? So 36 watt produced by this one and 18 watt dissipated by this one. So we have net power 18 watt. So what about the EMF of that battery? 1 amp is passing through that circuit, and the EMF of this guy is -5 volt. We have calculated here, put it there. So EMF of that battery -5 watt. This is negative because 1 amp current runs through the battery from the higher potential side to the lower potential. Okay, the polarity assumed for this battery was wrong, I have discussed. So we are storing energy in the battery as we charge it. Additional power is dissipated in the battery's internal resistance. So we have produced net 18 watt, okay? Some part is used to charge that EMF, and some power dissipated here, and some power will be dissipated here. So you can calculate all the things by using that I square R or I times EMF formula, which we have learned during the last lecture. Do you have any question here in that example? Okay, then let me continue with a complex network. It looks terrible at the beginning, but by applying Kirchhoff rules, it is very easy to solve it. So, figure here shows a bridge circuit of the type described at the beginning of that section I have shown you. Find the current in each resistor. Here we have current in the circuit. It is split into 2 parts, and we have another current here, and these are combined here. We have another current here, and then they are combined and traveling like this. So the question, find the current in each resistor. So what is the current here? 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 This is the question. And what is the equivalent resistance of the network of 5 resistors? Here we have 5 resistors. So what is the equivalent resistance of that resistors? So it looks complicated, but if you apply Kirchhoff's rules, then it is not complicated. So first of all, just try to apply the Kirchhoff's junction rule. So then we can get 3 currents, I1 here, I2 here, I3 here. Instead of using I4, I5 here, we will use junction rule. I2 is coming from that direction, I3 is that direction, then we will have here I2 plus I3, okay? I1 is entering, I3 is leaving, this one is also leaving, then this one will be I1 minus I3, okay? So now we have only 3 currents instead of 5 currents, okay? So we have increased the number of the target variables by using the Kirchhoff's junction rule. So now you can choose loops like this. One loop can be like this. Another loop can be like this, okay? So applying Kirchhoff's loop rule, then you can calculate the current in the resistors. So just apply loop rule to the 3 loops shown here. One loop is this one. This is one. Second loop is this one. I choose the direction of the loop. This is the travel direction. Second loop. And third loop is this one. You can choose another loop here. It depends on you, okay? This is the third loop. So now let's have a look first loop, this one. What do you see here? One resistor, another resistor, and we have one EMF, 3 circuit elements. So what about their contributions? So just start from the EMF, 13 volt. What about the sign, positive or negative? Since the travel direction from negative to positive in EMF, we have positive here. And what about the contribution of this one? This is the direction of the current. This is the direction of the travel. Travel and current are in the same direction. Then it will be negative, negative I1 times 1 ohm. And here, direction of the travel, direction of the current, they are in the same direction. Current is given by that expression. Put it there and equal to 0, Kirchhoff's loop rule. So now just apply same rule to the second loop, this one. Here we have again 3 circuit elements, this one, and this one. So just start with this one from here. You can also start from that one, it doesn't matter. Okay, so here, direction of the loop, direction of the current, negative I2 times 1 ohm, direction of the loop, direction of the travel, direction of the current, current times resistance, again negative because travel and current are in the same direction. And here we have EMF. Direction of the travel is from negative to positive in EMF. Then we have positive here, so equal to 0. Then apply the same rule to the third loop here. Okay, so let's start with that one. This is the direction of the current. This is the direction of the travel. It will be negative I1 times 1 ohm. Here, direction of the travel, direction of the current, again negative. Here, direction of the travel and current are opposite to each other. Then here we will have a plus. Then just make them equal to 0. By using the 3 equations, you can get I1 here. You can calculate I2. You can calculate I3. Okay, you can calculate I1 plus I2. Okay, so if you know the current traveling in that circuit, since we have calculated I1 and I2, then we have 11 amp passing through in that circuit between D and C. So I know the voltage difference here, then I can calculate resistance. And the resistance calculated here will give us the equivalent resistance of that network. Then this is 1.2 ohm. So by applying Kirchhoff's junction rule and loop rule, you can calculate equivalent resistance of a complex network of resistors, and you can also calculate the current on each resistor, and you can also calculate power of them. So here we will talk about a potential difference in a complex network. So in the circuit of example, this one here, find the potential difference VAB between A and B. So this is the question. What is the potential difference between A and B? So how to calculate it? The simplest path is through the center 1 ohm resistor here, 1 ohm resistor here. We know the current here, I3. I3 is already calculated. Okay, we know the resistance, then we can get the voltage difference between A and B by using that information. So if you would like to try other paths from this one to this, okay, you can also use other currents, okay, you can get the same result. I will not do that. So this is the potential difference in a complex network. So now let's continue with the electrical measuring instruments. So how to measure the currents, how to measure the voltage difference, how to measure the resistance of the resistors by using instruments. So we are using many electrical instruments. For example, this is a voltmeter, okay? This is an ammeter, measures the current. So both of them include a galvanometer. So now let's have a look to the working principle of the D'Arsonval galvanometer. This type of galvanometers measures the current that passes through it. So look at the picture here. I will try to explain from the basics. If you have any question, please let me know. Here we have a permanent magnet. This is magnet, okay? This is also magnet. This is shown by the gray color. And here we have a cylinder in the center. This is made from soft iron core. And we have this yellow wires, okay, coil wires here. Here we have a coil, which is also called as pivoted coil, made from conducting wires. And here we have a spring, which is shown by the purple color. And here we have a pointer, and this is the scale, okay? If this cylinder, let's say, turns around itself, this pointer also turns on the scale, okay? So initially, this pointer is showing 0 at the beginning, okay? But whenever a current passing through that coil, a magnetic field is produced, and then this pointer moves from 0 and it goes to its maximum value for the maximum current here, due to the magnetic field torque acting on the system. So this is the working principle of the galvanometer. If you remove the current, it goes back with the help of the spring here. This spring pushes back the pointer. Do you have any question here? Okay, you can also find many information in internet. There are also many videos, okay? So you can also see much more details about the working principle of these galvanometers. So now let me show you how to use them in ammeters and also in voltmeters. So both of them contains such galvanometers. So here we have an ammeter. Ammeters measure the current passing through it. So what we have here, we have a galvanometer. This part is galvanometer. This is the resistance of the coil. Here we have a coil, okay? Resistance of the coil is shown by RC, coil resistance. And current is passing through between A and B points, okay? Then we can measure the current here. But sometimes this current is huge, okay? Then we cannot measure it. In order to measure another currents which are higher than the range of this galvanometer, we can apply a shunt resistance here. What is shunt? In Turkish, it is also known as shunt veyahut da yan yol gibi in Turkish, okay? So normally we have this path from A to B, but if you add here another resistance, shunt resistance, what will happen? The current will be split into two parts, right? And one part of current will pass through on that coil on galvanometer, and another part will go on the shunt resistor. Is it okay? So what is the working principle? So this is the total current. This is the current, full-scale current can pass through on the coil, on galvanometer. This is the maximum current can pass on the galvanometer. This is the resistor of the coil here. This is the resistor of the shunt resistor. Then the current passing through on that shunt resistor is given by IA minus IFS, like this. This is the total current. This is the current passing through on that galvanometer, on the coil, okay? And we need that current. So by applying Kirchhoff's junction rule, you can get that the current passing through that shunt is given by that expression, IA minus IFS, okay? So since the potential between A and B and the potential here A and B are equal to each other, I can write the potential between A and B with that expression, IFS current here and the resistance here, okay? Or I can write the potential difference between A and B with that expression, current passing through on that resistor and the magnitude of the shunt resistor. Since they are equal to each other, I can get such expression. So if you know the full-scale current or the maximum allowable, maximum allowed current on the coil, if you know the resistance of the coil, if I know the resistance of the shunt, I can calculate this current here. So this ammeter can measure that current. This is the working principle of ammeters. Here we have one example. Do you have any question in that part? If you have any question, I can go into detail. Okay, then let's have a look at that example. What shunt resistance is required to make 1 milliamp 20 ohm meter described above into an ammeter with a range of 0 to 50 milliamp? So just try to understand. First of all, the resistance of that coil here we have a galvanometer. Resistance of the coil here is given, what is it? It is 20 ohm resistance of that coil. And the maximum current can pass through on that resistor is also given, 1 milliamp. But I would like to produce an ammeter in order to measure up to 50 milliamp. So maximum current here can be only 1 milliamp, but I would like to measure currents up to 50 milliamps. Okay, so how to do that? By just using shunt currents, we can do that. Put here a shunt current, then you can measure up to 50 milliamp. So the question is, what shunt resistance is required? So from that formula, we know the maximum current here, 50 milliamp. We know the maximum current here, which is 1 milliamp here. We know the resistance of the coil, 20 ohm, put it there, then I can calculate shunt resistance. Okay, so here we have done it. Shunt resistance is 0.408 ohm, 0.4 ohm, very, very small resistance, okay? So here we have 20 ohm in the galvanometer. Here we have 0.4 ohm. So you can imagine that many of the current will pass through on that shunt resistance, okay? Because the resistance is here very small compared to 20 ohm here, okay? If you calculate the equivalent resistance of this one and this one, they are connected in parallel. So you can calculate like this. Equivalent resistance will also be like this, 0.4 ohm. So at the beginning, resistance was 20 ohm, okay? So you cannot drive high currents, but by using shunt resistance, we have decreased the equivalent resistance of the system, and we can drive more currents, and we can measure higher current values. This is the designing an ammeter. And now let's have a look on voltmeters. Do you have any question here? Okay, voltmeter measures the potential difference between 2 points. We already know that. So if you use the same circuit, except this one, for this guy, you can calculate the potential difference for this one like this. This is the maximum current, full scale current, resistance of the coil here. And we know that 1 milliamp here, 20 ohm, put them here. So the maximum measurable voltage here is 0.02 volt, 0.02 volt, okay? So if you would like to measure much higher voltages, you have to connect another resistor here, which is a resistor in series, okay? This S shows us resistor is connected in series, okay? Not confused with the shunt resistor. They are completely different. This is shunt, but this is resistor in series. So what we are doing here, we increase the total resistance of the system. Here we have decreased the total resistance of the system. Equivalent resistance came from 20 ohm to the 0.4 ohm here. But here, by using an additional resistor, we will increase the amount of resistance of that system. So then the full scale reading voltage will be like this. This is the full scale current passing through on that circuit, and the total resistance of the system. Total resistance is given now RC plus RS, okay? Then since at the beginning, you don't have this one, okay? So you can measure limited voltage. But if you add another resistance here, huge resistance here, so you can increase the maximum measurable voltage here within the voltmeters by using galvanometer. So now here, let's have a look. Another example. What series resistance is required to make 1 milliamp 20 ohm meter described above into a voltmeter with a range of 0 to 10 volt. Normally, without this additional resistor, this galvanometer can measure up to 0.02 volt. But question asks that, can I design a voltmeter with the same device up to 10 volt? Okay, then you have to add a resistor in series. Okay, just apply that formula here, and then we can find the resistor in series is almost 10 kilo ohm. Okay, so you increase the total resistance of the system up to 10 kilo ohm, then you can increase the total measurable voltage of the system. Okay, so this is designing a voltmeter. Now I would like to show you a bio application, electromyography. Maybe you know this one from EMG name, in Turkish EMG, okay, in hospitals. So here you see a hand of doctor or nurse. Here we have an EMG probe, and this is the hand of the patient, a fine needle containing 2 electrodes like this, okay, 2 electrodes like this here on that needle is being inserted into a muscle in this patient's hand by using a sensitive voltmeter to measure the potential difference between these electrodes. A physician can probe the muscle's electrical activity, okay? You insert this one, and then you can measure the muscle's electrical activity. This is an important technique for diagnosing neurological and neuromuscular diseases. This is a very nice example of voltmeters, precise voltmeters, let's say. So now let's have a look how to use ammeters and voltmeters in combinations. If you would like to use them together, you must be very careful. You can measure resistance and power here. So ammeter measures the current, voltmeter measures the voltage. Then you know the current, you know the voltage, you can calculate the resistance. Or you know the current, you know the voltage, you can calculate the power of the system. But you must be very careful when you are using ammeters and voltmeters in combination in the circuits. So why? In reality, these ammeters are considered that they have no resistance in ideal ammeters, okay? But in real cases, they have also some resistance, okay? So for this reason, if you would like to measure the voltage of that resistor, potential difference between A and B, you can measure like this. You can measure from A and C, okay? So this is the current. Ammeter will measure the current passing through on that resistor, and from A and C, you will measure the voltage. But here, the problem is that normally, let me choose pen here. Normally, this resistance of the ammeter must be 0. For this reason, the voltage difference here, we have current, but since the RA is 0, then the voltage from the ammeter will be 0. Then this voltmeter will only read voltage difference from that resistor, okay? This is in ideal case. But in reality, it does not work like this. Let me clean first and then continue. So in reality, these ammeters have also a certain very small resistance, and then they also contribute to the voltage, okay? So the voltage measured here contains contribution from this one and this one. You must be very careful. Or you can use them in that combination. Here, we put voltmeter between A and B, and we put ammeter here. Okay, now you measure only the voltage difference between A and B. That's nice, but what about ammeter? Ammeter measures the current is coming from the resistor, but there will be also another current which is passing through on the voltmeter, and you will measure here total current coming from that direction and that direction. In ideal voltmeters, the resistance of the voltmeter must be infinitely large. We have discussed during the last lecture, right? But it is not in real cases. For this reason, very small amount of current can also pass through on the voltmeter, then ammeter will read both of them, okay? You must be very careful. So now let's continue with ohm meters. Ohm meters, they are used, of course, to measure the resistance, okay? Here we have a resistor, and you can measure the resistance of that resistor. So this is the design of an ohm meter. It consists of a meter. This is the galvanometer, a resistor here, and a source. Here we have a source, EMF source, often a flashlight battery. Here we have a battery. They are connected in series, okay? So resistor, galvanometer, and battery, they are connected in series. So if you connect between X and Y, there is no resistance at the beginning, let's say. This is nothing. And here we have a connection shortcut. we have a current passing through on that circuit, okay? The resistor here has a variable resistance, as indicated by arrow, variable resistors indicated by arrow through the resistor symbol. And first we connect X and Y directly and adjust this RS until the meter reaches 0. So let's consider that here at the beginning we have very small resistor, very small resistance. And since it is adjustable, you increase the amount of the resistance, okay? So now resistance becomes huge and no current can pass through on that circuit and you see 0, okay? So you adjusted the resistor and you connect another resistor here in series, then it shows some certain amount which is giving us the resistance of the resistor. This is the working principle of ohm meters. And so here we are using a galvanometer. Here we are using a galvanometer. Here we are using a galvanometer, okay? But in digital multimeters, we are using integrated circuits and they provide much better and much sensitive results. So, and they can also measure voltage, they can measure current, and they can resistance over a wide range together, okay? So here you see a digital multimeter. Here we have a red region. It measures voltage, AC voltage here, I think you can see, and here DC voltage. And in the yellow region, we can measure current. This is the AC current, this is the DC current range. You can adjust which range you need. And then this green range shows us the resistance, and you can measure the resistance from 20 ohm to 2 mega ohm, okay? So this is conventional digital multimeter. Okay, I will finish with the potentiometer. We have enough time. I think I can finish on time. But if you have any question, please let me know. So potentiometer is an instrument that can be used to measure EMF of a source without drawing any current from the source. The term potentiometer is also used for any variable resistor here, okay? Here we also have another variable resistor. It is shown by the arrow, okay? Look at that one. This is circuit symbol for potentiometer, also called as variable resistor, this arrow. So what is the working principle of a potentiometer circuit? This is a potentiometer circuit. Here we have an known EMF, EMF1, and here we have a potentiometer or variable resistor, and here we have a galvanometer. Galvanometer has certain internal resistance, coil resistance, okay? And here we have another EMF, we don't know, unknown EMF. We would like to measure it, okay? We would like to measure the EMF of a source. Potentiometer can be used to measure the EMF of a source. And here we have a EMF. We would like to characterize it. We would like to measure its EMF, okay? How to do that? This is known EMF, and we have current from positive to negative within that circuit, okay? So this is the current direction. So here we have an adjustable resistor. Adjustable resistor means that, for example, if you put that C point here, the current will be split like this, okay? But so here there will be like shortcut, no resistance of it. If you put this C point here, there will be no resistance in between and current can easily pass through. But whenever you move C point to the right side, you will get resistor, okay? So current will go in that direction, but in order to come to that line, it will see some resistance, okay? So if you further increase that resistance, then finally there will be no current here. This I2 passing through in that circuit will be 0, okay? So in that case, put a known EMF here, then galvanometer will show you some result, and then remove that known EMF and put another unknown EMF, then you can measure the potential difference between the terminals of the EMF. This is the working principle of the potentiometer. So with that one, I have finished the lecture today. And on Thursday, I will continue with the RC circuits. We will talk about charging a capacitor, charging or discharging a capacitor, and we will talk about decreasing of the currents by time within such circuits. Do you have any question in that part? Any question? Okay, then I will close the session. See you then. Kendinize iyi bakın.